All right, so now we're looking at groups. This is actually section 4.7 from the syllabus, but in your book it's section E. So skipping around a little bit in the syllabus, but we're going to talk about definition of a group, Latin squares, abelian groups, and the examples of groups we're not going to talk about so much. Those will come up as you're practicing problems and in some of our examples. Nice applications over here if you're looking at it. I love when they bring up the Rubik's Cube as actually fitting into math contexts. All right, so let's start with defining what a group is. So basically the way that we get a group is we take a set and then we link that set with an operation. So groups start with sets plus an operation. And then there must be a few certain requirements. So we also have, and this is very important, our set has to be closed over the operation. The operation is associative. And this is, of course, all typed up nicely in the nice notes with all the math definitions as well, so you could look at that. The set has to contain the identity element of the operation. So set contains the identity. And also for every element of the set, there must be an inverse. So I'm going to say for each G element in the group, so I'll talk about group here, we have G inverse such that G operation G inverse gives us the identity element. Okay, so we start with our set and our operation, and together those things make a group. Normally we show the group using G, comma, star, but you can also just write the letter G for talking about the group. And groups, of course, can be finite or they can be infinite. We can have our group be infinite, and of course, if we look up here at our examples of groups, we've got all of these are infinite groups, right? The real numbers, rationals, integers, complex numbers under addition. So all of those are that's an example of a group. It would meet all these conditions. Okay, so let's look at an actual example of a group. So we can look at multiplication over complex numbers. So I'm going to make my set be 1, -1, I, and -I. Okay, so I'm going to make my Cayley table. Multiplication, 1, -1, I, same thing. All right, so in my Cayley table, of course we've got 1, -1, I, -I, -1, 1, -I, I, I is -1, -I squared +1, I, +1, -1. Okay, so is it closed? Yes. Does the set contain the identity element? Yes, our identity element is 1 in multiplication, of course. For every G, is there an inverse? Well, I can see for each row and each column, I end up with a 1 somewhere. So the inverse of I would be -I, inverse of -I would be I, of course. We've got that in both places. So for every element, we do have an inverse, so we meet our conditions of a group. Yeah. So I'm going to stop the video here, and I'm going to come back and also talk about this Latin square idea. So this is a group because it meets these conditions.